Is lecture 6B from MSE 5033 Composite Materials. We have been talking a lot about processing and making different kinds of composites and so on. Now, let's switch gears a little bit, talking about mechanical properties, talking about properties of composites which will be related to design with composite materials. Now, if you had fibers that were in the uh, 0 degree direction or the direction of the stress, and as long as you are below the elastic limit of the composite material, you're probably not going to have any kind of failure at all. So this will be a crack-free type of a composite. In the case of a metal matrix composites or a polymer matrix composite, if the stress exceeds a certain limit, the fibers or the matrix can start cracking and you are going to see lots of cracks in the material. Now, supposing that only the fiber were to break, that is, we are exceeding the strain of the failure strain of the fibers are going to start breaking, but still the material still holds together. And this is the type of microstructure that you will find. In the case of ceramic composites, ceramic matrix composites, you are going to have two cases. One in which the interface is very strong, helps to bond the fibers pretty strongly with the fibers, or the fiber matrix interface is pretty strong, or you can have a weak interface between the matrix and the fibers. So if you have a strong interface, most of the time this material is going to break like a brittle material, so you're going to have a flat failure. But if you had um, a weak interface, after the matrix starts breaking, the fibers are still going to hold together and hold the whole component together. So then it starts pulling in and out of a fracture, and the cracks are going to get deflected along the interface, and this material is going to be a tough material. Now, if you look at the stress strain behavior or the stress strain curve of a unidirectional ceramic composite, even if the matrix and the fibers were brittle by themselves, when you put the whole thing together, it starts showing a damage tolerant behavior. If you plot the tensile stress versus tensile strain of a composite material, what happens is that till the elastic limit, the stress strain behavior is going to be a straight line. Now, beyond that, the fibers are going to start holding together and it is going to let the cracks get deflected and absorb most of the failure energy. But what is to be noted is that this composite material is going to be can be used to design for stresses only below the matrix microcracking stress. But it might have a pretty high strength by itself. But because of these cracks and so on, you are not going to be able to use it beyond the matrix microcracking stress. If you plot the flexural strength versus fiber volume fraction, especially for uh, a composite material, what happens is that it's supposed to be a straight line behavior between the failure's flexural strength and the fiber volume fraction, or the tensile strength versus fiber volume fraction. But there is going to be a lot of scatter. And that scatter is mostly due to matrix porosity. So if there is porosity, you really cannot predict how the material is going to behave. So porosity in in composite processing is a big deal. So that's related to the homework assignment that I talked about in the first part of this lecture. If you plot the Young's modulus versus the fiber volume fraction and you apply the rule of mixtures, then it is supposed to be a straight line behavior. So, but it is not going to be um, exactly fall on that line. And again, that is mainly because of the matrix porosity. Now you can see that these lines will start, these points will stop showing any kind of actual experimental values beyond 60% because processing these composites beyond 60% fiber volume fraction is going to be a real hard thing to do. You can also try to plot the creep behavior of these composite materials versus applied stress or time. And what you will find is that you can have a straight line behavior and you can predict the steady state creep rate versus stress. And as expected, if you start increasing the stress, you are going to start seeing an increase in the steady state creep rate. So that means these materials will fail faster as you increase the increase the applied stress. Now, looking at looking at ceramic composites itself, which is a very important part of these different types of composite materials. The energy dissipating mechanisms in ceramic composites is a very important phenomenon to learn and to understand. Now, there are many different types of energy dissipating mechanisms in ceramic composites. Now, if you had the fibers and they were to pull out from the matrix, suppose there is an advancing crack and these fibers are supposed to pull out from inside the matrix on the opposite side. So the energy can be dissipated purely by fiber pull out, or if you had, say, fiber bridging and they would be going back and forth and dissipate the energy that way. Or if you had interface were to debond, the interface is weak and it were to debond and to deflect the cracks along the interface, that could be another way of dissipating the energy. The fourth one would be to purely deflect the cracks by itself. Now, the most energy is dissipated in the interface debonding and crack deflection mechanism. You can also have the standard crack pinning and deflection mechanism in ceramic composites. So this one shows you a cross section of a hot pressed nickel on fiber glass ceramic. It's a Cylon composite. They call it Cylon, silicon aluminum oxynitride or oxynitride type of composite. And you can have different mechanisms for energy dissipation in these materials. For example, if you look at the fracture surface itself, you can see that the fibers are pulled out of the matrix on the opposite side. So this is one major mechanism for toughening of these materials. And this is also because the matrix, the interface is actually not very strong and it is allowing the fibers to pull out. Now what happens is that beyond a certain point, the fibers are going to break, and you are going to have, suppose these cracks were moving from left to right. As it is moving, it is getting deflected along the fibers. Then these fibers start holding up the load, and then these fibers break, and so on. And so the crack starts moving from left to right by various mechanisms of energy dissipation. If you had a pyrolytic carbon coating on a silicon carbide composite with nickel on fiber, which is also silicon carbide, you will find that there is quite a bit of fiber pullout. So you can see the amount of fiber pullout, and this is because the carbon coating on the nickel on fiber itself is pretty weak, and it can help this composite to dissipate quite a bit of energy. But what happens is that if you start plotting the fracture strength versus test temperature beyond a certain point, in say, for example, silicon carbide viscous reinforced aluminum. By the way, just to point out, there are not too many composites with viscous reinforcement in use in today's applications, and that's because there is quite a bit of issue with the use of whiskers, because those whiskers can lead to things like silicosis and so on. So you want to avoid those kinds of health effects. So you may not find too many composites with whisker reinforced material, whisker reinforcement. But if you plot that, you will find that beyond a certain point, it starts degrading quite rapidly, because there is no fiber reinforcement, and it is quite weak beyond a certain temperature. So beyond 950 degrees centigrade, you really cannot use this composite material. Now what you will also find is that you can also calculate the fracture toughness of these materials. So beyond a certain, it keeps monotonically increasing up to about 20%, but beyond that it starts leveling off. Now for ceramic composites, there is also another phenomenon called R-curve behavior. So I'm not going to cover that in this class, but I want you to be aware that such a mechanism exists in ceramic composites. So there is how do you know whether the fibers will break or whether the interface will debond and allow the crack to deflect along the fiber matrix interface bond? So that is decided by the correlation between the energy of the interface versus energy of the fiber versus elastic mismatch. So if you can plot that, so this is the point at which the interface will start breaking, and this is the point where the fiber will start breaking. So if you go beyond that, then this material will fail by fiber failure, whereas in this case, on this side, it will tell you that it will fail along the interface. So if you can define the properties of the fiber and the matrix, then you can calculate which one will control the failure behavior of these materials. If you had a composite, say alumina, tin oxide, there could be some mechanical interlocking at the interface that can lead to a failure, um, which is more along the lines of the debonding. If the interface were pretty rough, what happens is that there is as the fibers are pulled out of the matrix, there is a lot of energy being dissipated because of that interfacial roughness, and that can lead to enhanced toughness of these materials. If you had a completely smooth interface, then the interface is going to fail completely, and these fibers are going to pull out till the point at which the fiber will start breaking out. I don't remember exactly which composite material system this belongs to, but there are, this could be uh, a carbon coating on a carbon fiber or a nickel-on type of a fiber. Now, there are several advantages for, we have talked about this previously, they have several advantages for composites versus conventional materials. So if you have a completely random orientation, say a chopped fiber orientation, um, it may not give you the same properties, as good properties as continuous fiber reinforcement, but still it is better than having a completely brittle matrix. So this one is silicon carbide whisker reinforced alumina composite, and there are many different types of applications for these composite materials. For example, um, in the one of the earliest applications was for these materials was for use as a flame holder from a turbine engine. So as the flame is coming out, um, if you are having a metal component, that metal component can easily melt away completely. But if you had a ceramic composite, especially one which had very good thermal expansion coefficient capabilities, then it can easily withstand the flame and allow these parts to be held together for multiple times. So some of these applications are, like for nuclear fuel holders, um, flame holders, and so on. Or, for example, there are some applications where you have very fine filters and so on. So one of the special types of composite materials is carbon-carbon. I don't know if you know this or not. Some of the earliest successes of the space shuttle program was because of the capability of carbon-carbon composite materials. And these carbon-carbon composite materials are made by a specific type of process. Now, these are also being used in missile nozzles and so on. So what you do is, this one carbon fiber is not continuous fiber, so they are carbon fiber, or they could also be continuous fibers. But carbon fiber, you make that into a preform and you infiltrate that with a pitch or resin. You cure that at a temperature of around, say, 350 degrees Fahrenheit. You get a polymer matrix composite then you have to carbonize it at say around 1100, 1200 to 1600 degrees centigrade. You get the carbon-carbon composite material. During the carbonization process, this polymer, the matrix will shrink quite a bit. So you will end up with something like 60 to 70% volume yield. So you are going to get 30-40% porosity. Then you have to re-impregnate that material with the matrix, only the matrix resin, and then you have to recarbonize it. And this process may have to be repeated maybe like 10-12 times. So one of the reasons why carbon-carbon composites are expensive is because of this re-impregnation and pyrolysis that has to be conducted multiple times. You can also do what is called chemical vapor infiltration processing. So you can have the preform and you do the CVD or chemical vapor deposition or chemical vapor infiltration multiple cycles to get full densification. In this case, the advantage is that you can get almost 100% densification compared to the this kind of a process. So this one is if you had, there are different kinds of impregnation and pyrolysis cycles that you can do, and it can lead to differences in properties. So if you do the carbonization at atmospheric pressure, it may not give you as good properties because you will have a lot of porosity left behind. But if you did by hard isostatic pressing, an impregnation process, then you can have almost 95-98% densification, which will give you much better density and mechanical properties. Now, if you have carbon-carbon, I don't know if you know this or not, carbon by itself in an oxidizing atmosphere will burn at around 400 degrees centigrade. So if you have to use these materials in an oxidizing environment, then what you have to do is you have to put what is called an oxidation protection coating. And this you have to do even in the case of ceramic, other ceramic composites, say silicon carbide composites, you have to do that. And the reason is because when oxygen comes in and starts burning, there is a difference in carbon content from the top to the bottom. So there is a diffusion process taking place. Oxygen will diffuse in and start burning up the carbon. So that will reduce the mechanical properties of these composite materials. So in order to prevent that, you have to put what is called an oxide coating or an oxidation prevention coating. And most of the time it is a multi-layer coating, and you also have to make sure that it is well adherent to the underlying substrate material. So this is a research topic by itself, and there is a lot of work being conducted, and I don't think that they have really come to a satisfactory answer at this stage. So in this case, what they do is they have boride or boria, then they put what is called an oxidation barrier, then they put an borosilicate overglaze, and that prevents. Now this itself is much thinner than the substrate itself, and it will give you good properties. Switching gears again a little bit, there are different kinds of fabric that you will find in literature. So the most common one is a two-dimensional fabric. So in this case, there are carbon fiber toes. Now, each of these toes, I mean, there could be something like 5 or 6 toes, and each of those toes will contain something like 1,000 to 10,000 strands of these materials. And each of these toes is, you you weave them alternatingly. Now this is called a plane weave, where the one toe will go up and down the next toe that is going in a horizontal direction. So this is called a plane weave fabric, and we call this a 0-90 fabric. 0 for this direction and 90 for this direction. You can have variations of the plane weave, and we will this is a variation. So in this case, these 0 fibers will come up one time, and then it will go down under the next toe only after going over 5 of them, and you do the same thing on the opposite side. Okay, so this is called a 5 harness satin weave. You can also have an 8 harness satin weave, and these are all different varieties of composite materials. And you can also have a separate toe material that is going in the thickness direction. So if you have fibers only in one dimension, it will have the properties that is related to these fibers in the 0-degree orientation. So you are going to have pretty strong material, but then it starts weakening and start breaking down. But if you had fibers in both the 0 and 90 direction, then it will start showing much better composite behavior. And if we had fibers in the 3rd dimension, then you can have a 3D fabric. So this one closely relates to stress strain behavior of a metal type of a material. But the problem why we don't use this 3D fabric most of the time, unless the application really demands that, is because of the cost associated with the 3rd dimension of the fibers. So these are all some of the applications, like you can have a frustrum made out of a carbon-carbon composite material. This one is an aircraft brake made out of a carbon-carbon composite material. And you know that these materials can take up quite a bit of heat and pressure. So most of the aircrafts, these brakes are made out of carbon-carbon materials. And one of the major producers of carbon-carbon is called is from France. I believe that the name of that company is called SEP, and I believe that they have a collaboration with GE for making some of the components for the Gen X engine. You can also have molds made out of carbon-carbon composite materials. So you can have multiple types of applications for composite materials, and we have only scratched the surface of these applications. Okay. So that's about it I have for lecture 6, and we will do the others before the end of this week.